everyone, I'm Xinyi, a PhD at the University of Utah. Today, I'm going to present a tool to help capture the exceptions, the floating point exceptions in GPUs. Our work has already published in PLDI 20 in the SOP workshop. When it comes to the floating points issues, most discussions will circle around the notions of the error. However, an FP program that meets all error bounds can still be wrong. So how this happen? This is because a number may exceed the representation ability of the floating points, resulting in special values, then infinity and subnormals. Output may look normal, yet computation may have gone undefined inside the codes. The IEEE standard has defined 5 classes of exceptions, which I have shown here, that can result from arithmetic operations. Note that, except for the inexact exception, the rest of the events will result in either a non-infinite or a subnormal, which is a number smaller than a normal floating point number, but that is not zero, those special values. These exceptional values cannot be ignored because they may propagate through the programs and result in invalid numbers. As suggested in IEEE standard, the series exceptions must be reported, include the overflow, divide by 0, and not a number result. Life is easier for CPU programs with respect to the floating point exceptions because they can rely on hardware traps generated by CPUs, not only to detect exceptions, but even correct them at the running time. However, for NVIDIA's GPU users, there's no way for them to know if those exceptions happened in the device. In their official document, they have already mentioned their hardware didn't support trap handlers for floating points exceptions. Instead of hardware handler, exceptional values can be called in software as the figure shows. That is how we detect floating point exceptions in GPUs with our method, with our tool. Though the software exceptions detection may slow down the execution, FP exception detection is important. Optimizations, precision tooling, unseen new data, and extra may all generate exceptions that may crash our final results. Moreover, considering closed source CUDA libraries and the NVCC compiler optimizations may be used in the GPU programs, it is important to detect the exceptions at the binary level, like Professor Linda mentioned before. That's why we want to use the dynamic binary instrumentation tool, NVBit. In fact, we have already used our tool, being FPE, to detect exceptions in some widely used GPU benchmarks that haven't been reviewed before. This is the detection table which is presented in the paper. We can see that we have detected exceptions in 5 programs, which is notated as red. One thing to mention is that this is just the preliminary results. For example, we can detect more exceptions in the Graham-Smith program currently. Here I want to use the Graham-Smith as an example to demonstrate the importance of floating point exceptions detection. Graham-Smith is a program to generate orthogonal vectors using the Graham-Smith process. It is used as an essential kernel in many scientific computing applications. As you can see, the program just announced kernel 1, 2, 3 in order recursively as k increases, gradually fill the array ARQ. This is the exceptional messages printing with our tool. We can see that an infinity and the division by 0 will happen in kernel 1 and kernel 2, where the values R, Q will be used in the following computations, raising more nths and infinities. If we enable the comparison function embedding in the program, we can see the final values in A array computing with GPU mismatch the results from the CPU. So with so many nths and infinities in the codes, that may be the reason that they are mismatching. Now I want to give a very simple description about the overflow, the workflow of the Bing FPE. Similar to other NVBit tools, Bing FPE intercepts CUDA driver API calls, inspects instructions, and performs instrumentation when necessary. It also relies on the node preload to load the shared object files before any other libraries. First, our tool Bing FPE will inspect each FP instructions when a kernel is launched. Later, it will inject the instrumentation function to collect the values stored in the destination register, send back those information to host, and perform the check and print them in the host. Here are some related work relating the FP exceptional detection. The FP checker intercepts the LLVM layer, so it can only detect the exceptions in CPU and GPU programs which compiled with Clang. FP spy can detect the exceptions if CPU using the trap in CPU using the trap handler. More work is ongoing. We are working on to scale the Bing FPE to handle large codes. So I think that's all for our Bing FPE 2. Is there any questions about our work?
Thanks very much for the talk. It looks like Laura has a question right away.
Okay.
Hey, very nice talk. And yeah, I have a question. So
Sure.
from my understanding, you detect this exception for a certain input value. And
yeah.
have you thought maybe to apply techniques such as the one, for example, using S3 for code, like using abstract interpretation techniques to do like static analysis, so you can reason about like you know, any possible input, or maybe intervals, or maybe other techniques that I don't know, such as symbolic computation.
Symbolic, yeah. Yeah. So so for now we just use the dynamic analysis. So the symbolic one, we have considered it. Probably we could do it in the future, but even the dynamic one is valuable because we have found in many machine learning programs, they are using the GPU to speed their codes. However, when they cannot test all the inputs, so when some users are using their models to train their data, they find, okay, there are some nths in their final results. So probably our tool can help them to find why this happened in some specific situation.
Yeah, if I can add, thanks, Laura. This is a great question. So what we did was to actually run it on the data that came with their code. So at least if they had tested it on their code and found the nans, they would have stopped, but they didn't. So that is something that tells us that we didn't go beyond their data sets. The second is Ignacio has a paper coming up in Supercomputing 2022 where he's using Bayesian optimization to search for possible inputs. So this could be an approach that one can consider. Okay, I'll ask Ignacio to post it when he's ready. Thanks. But there the problem is we need to know the input, and he applied it to arithmetic libraries, and libraries, the inputs can be anything. So that's the reason why we could go there. Yeah, thanks.
More questions for Xinyi? Another thing I was a little bit curious about is what, it seems tricky to work on these kinds of projects because as is going on in the chat here, there's a lot of diversity among the target accelerators. Is there any, like, what's the, I mean, these tools help, but what is your experience day to day trying to build on this stuff? Was it hard to build the tool and debug the tool itself? Are there things that would help make this process easier? I think we're sort of still just at the tip of the iceberg of all these challenges, and having tremendous diversity in, traps versus exceptions versus nans versus signaling and all this stuff. I was wondering if you think sort of more broadly on where this is all headed.
That
was a vague question. Yeah. So what's next, right? You talked about BenFPE, and so there's sort of these direct extensions, but where's it all headed? I mean, are we going to eventually settle where all the accelerators are going to have a consistent interface for exceptions and traps, or are we going to live in this world of tremendous diversity? I'm just wondering if you have, having worked on it, some takes, some speculation on the future.
Yeah, so we are working on a similar. We are working on extending the BenFPE, and we want to. We want to develop it as a debugger to in the future, to help the users which are using the GPUs to find the. So as the chat said, we know where the exact locations of these exceptions. So probably if we see some nans in the final result, we can use our tool to debug why this nans happened, how it propagates, and probably the designers can help fix them or explain them. That is our plan for now. Yeah.
Yeah, it's a good answer. Yeah, I would also note that AMD advertises floating point traps, and I don't know how they managed to pull it off with the hardware cost of generating traps from all the threads. And AMD has a very clear specification of their floating point, much clearer than NVIDIA. So I can paste the link here. Yeah. But unfortunately, only some large-scale HPC projects, exascale project, is going to run on AMD. And that's not enough. We need to populate the world with more such hardware. I don't know about Intel. You guys can tell whether there is a precise trap handling. Yeah, but it's kind of antithesis to GPU model. GPU model and traps don't live well. So
yeah, I am in Intel graphics, so I'm not going to diverge future secrets or anything like that, but it is very interesting you talk about this, because I will touch on this in a few minutes, but also, so just like one general question, is this a broad endorsement of like NAN and infinity and the ability of IEEE exception things to actually find bugs?
Sorry, can you say it again?
Would you say yes? Would you say that the IEEE 754, that extra crap that Florent was talking about this morning, that people were complaining about, the positive people complain about makes IEEE hard to implement, but they found actually doesn't. But would you say that NANs, infinities, exceptions, is this actually helpful in catching bugs in real code?
Bugs. While Xinyi is thinking of the answer, I'm going to think, but I'll say one thing. Actually, there is a mixed library called APEX, an adaptive mixed precision library, where NVIDIA uses it in the feedback loop. So they scale the derivatives till the exceptions go down, and so they can set the knob based on the number of nans.
Okay.
So there are things, active usages within mixed precision libraries, but
okay. So
whether that is a good feature or not, I don't know.
All the fighting with the exceptional cases and the flags is not in vain. That's good to hear from somebody, because a lot of the time in software land, it's just like, oh, what's a floating point flag? How do I even read that? That's not exposed in Python. So it's cool to see it.
Xinyi, you can type your answer in the chat if you like. If you have any other answers.
Okay.
So